All right, I quickly realized something. With this test pattern here, it's not quite enough, right? It's completely symmetrical, which means if our mapping algorithm is somehow off, for example, maybe inverted, we're not going to notice when it gets invertedly mapped over here. So to fix that, what we're going to do is we're going to go into our code, and really quick, all we're going to do is kind of like add some like quadrant coloring to the pattern, right? So let's see. Here's our pattern. Okay, here's where we're sampling. And let's say, how do we want to do this? Let's say color. We'll just put a. Oh, we can't do that. Well, let's just do RGB like that. And we're going to add like another check. Var. So usually I would not RGB. Usually I would not do a compound declaration like this, but just to save some space, since it's kind of precious right now, I'm going to do a compound declaration like that. And we just want to know if we're on the left or right of the center point, right? So if x, and we're not going to be perfect about this, so, right, if it's on the midline, do I really care if it's one color or the other on the midline? Not really. So, if x is... sorry. Let me think. Okay, so distance is absolute value. So we're thinking about the x, and the x in terms of where the center is. Okay, so if x is less than cx, we use one color, otherwise we use another color. Do you want to get fancy? Do we want to get fancy and do like a ternary expression? Because we can. I mean, it's JavaScript, right? So we could do something like r equals x less than cx, question mark, and if it is, red is, I don't know, 64, 32, I don't know. Otherwise, it's like 128 or something, right? We can do that. R, G, and B. So we want a different color. So we got our right and left, and then we want something for Y. So CY, we want a different color for the green, and then for blue, what do we want to do? Blue we could do based on the distance from the center to get some type of nice little gradation color. Really quickly, how could we do that? I don't know, let's just do something really simple. We'll do like the distance times, I don't know, 64. No, not something that big. Times 16, and then we'll modulate it by 256 to make sure that we never get a color value higher than 255, right? Because once it hits 256, it goes back to 0, right? So 256 modulo 256 is 0, right? So this is going to ramp all the way up to 255 and then reset. Okay, so R, G, and B. And we have R, G, and B, right? So it has to be within the ring. And if it's inside of the ring, we're going to give it some fancy coloring. So let's check out our canvas and refresh. All right, cool. So we got like a little, almost looks like a Simon Says kind of a pattern, right? We got these repeating rings. So now, like, when we map this shape over to this viewport, if we accidentally mirror the design, it's going to be obvious, right? Because then the blue will no longer be in the top left if it gets mirrored, right? If it gets mirrored on the X, the blue will be on the right side. If it gets mirrored on the Y, the blue is going to end up on the bottom. All right, so with that, we should do some sampling code. Let me see how long I've been running for. Only 5 minutes. Okay, yeah. So let's write some sampling code. So first of all, I'm not really sure what the logic is going to be. I just know I want something that's going to... It's going to use this canvas to sample from another canvas and then populate this canvas. So let's say... so it's... I'm not sure what I'm going to call the function. I guess it's like map pixels from A to B, map pixels from source to destination, or we could just call it map pixels and then put in the comments from where to where. Okay, I like that, so let's go with that. So we're going to say map viewport pixels, or let me think. I don't know. Okay, whatever. I'm just gonna be really generic. I'm just gonna call it do mapping. Because, you know, I can come up with a better name later. And let's say we want our the rectangles, correct? Source rect. Okay, so I try to be general to specific when I can with my variable names. So therefore, DST. So see how these are the same, right? So that's signifying to me that within this context, rectangle is the generic part, and then we get more specific. Okay, generically or vaguely, it is a rectangle. Okay, but give me some more information about the rectangle. Give me more details. So generally a rectangle, specifically the source rectangle. Generally a rectangle, specifically the destination rectangle. And then also when I'm looking at code, the deltas or the diffs are all in the same place, right? So when I want to see what's different about these two variables, I can just look at the ends, right? I don't have to look at the beginnings. Okay, so the source, and then we can also write like this, source rectangle, just some long-handed comment, and then destination rectangle. And then I'm just gonna, because I'm OCD, what can I tell you? So we're gonna do mapping from one rectangle to another, and we want to, you know, map pixels, so we're going to need this canvas adapter. So we noticed that in all these other functions, we're using canvas adapter as the first function. So we should, sorry, did I say first function? I meant the first object, the first parameter, whatever. So let's keep that consistent pattern going, right? Because yes, we could put it here, but we want to keep something consistent, right? The more the more consistency we have, the less we have to remember. Right? Like if you ever worked with like a really good library, you don't know the name of a certain function, but you can like guess at it because of the consistency. That's kind of what we're trying to go for here. Okay, so we have this do mapping function, and what we can do right now is we can take the call and we can use that to start our function body down here. So we'll just paste that there. And we'll say function do mapping. I haven't been indenting any of these other things. So should I don't know. I don't know. Let's not worry too much about that. If I should, because I don't know. Does it look better this way or this way? I actually kind of think it looks a little bit better this way. I I like to over indent and then make my code really terse so I still don't go over my column limit, even though I'm indenting a lot. Okay, anyways, so we had our function call, and we want to sample. So here's our source, here's our destination. So this is like from and then to. Source, dest, does that make sense? All right, sure, why not? So rather than type stuff over again, I know we have a loop that we already kind of wrote that in, so we can go down to that loop. Oh, there we go, right there. So we're just going to take that code, and then we can just paste it right here. Obviously, it needs a little bit of changing, because now it's called, we're going to loop over every pixel of the destination. And why do we want to do every pixel of the destination? Right, because the other... So there's two ways we could do it, right? We could loop through every pixel of the destination, sample from source, and then put a color in the destination, or we could loop over every pixel of source, and then write to the destination. Right? Two different ways you could do it. But there's a very specific reason why we want to loop through every pixel of the destination. Because this destination here is eventually going to be like the main viewport in some type of like OpenGL shader code, right? I'm just testing out some like algorithms that I'm eventually going to put into like some OpenGL code. So this is going to be like the OpenGL rendering context. And this viewport over here is actually going to represent some like data inside of a texture that I want to sample with some shader code, right? So because we're kind of thinking in those terms, we want to write the math for these algorithms in a way that's going to best adapt to bringing it over into OpenGL after we've, kind of figured it all out. The question is, well, why don't I just start out with OpenGL? Well, I don't know, maybe I want to take this over to Vulkan. Maybe I want to do it in OpenCL, but right now, I just want some type of environment where I can prototype quickly. And I will tell you that writing C code and even OpenGL code, right, they're all a little bit more difficult than JavaScript. So I'd rather just hash out the math in JavaScript first, and then write it again in those other languages after I've kind of hashed out the math. Okay, so we've got our destination viewport. We're going to loop through all of those pixels, and we're going to sample the pixels. And so the first thing I'm thinking is we probably need some code that actually samples pixels, because we have like a thing that puts pixels, but we don't really have a thing that samples pixels. And we're going to put that functionality into our adapter. So we got our canvas adapter, right? We got our public putPix function. We got apply. So what we really need is getPix. I like to use the word get instead of set, because, hold on, getPix. So if you use like, if you use get and set instead of put and get, notice that the difference between put and get, there's two letters that are different. Whereas with set, like get and set, which is typically what people do, getters and setters, right? The only difference is a G, right? So I like there to be as much like contrast as possible. So I like terseness in my variables, but I also like, there to be contrast. So now these variables are more different, right? there's a 2/3 difference between the variables instead of a 1/3 when you use a get and a set. So I use put and get instead of get and set in my code. Anyways, so let's look at put picks, see what that does, and we probably can base our get picks off of that. So we'll call this get picks, and right off the bat, we know these R, G, B, and A. We can probably do something like this, where we return an array that has R, G, B, and A within that order. That's probably not the most efficient way to do it. Like, the most efficient way would be to use something called an output parameter, where the last parameter is a pass by reference object that you're going to populate with the value. You know what? Especially because we're going to do this for every pixel, and that could be called millions of times. I'd like not to be completely wasteful and keep on constructing new arrays. So what I'm going to do is I'm going to say RGBA out, like that. Or I could say out param RGBA. I don't really like to be that terse, though. I'm just going to say since I'm going to keep to my pattern of, my pattern of 3 by 3 for my variable names, call it out RGB, even though it has RGBA in it. And I'm just going to, do this. Now, do I want it to just be an array that gets inputted, or do I want it to actually be an object? Yeah, that's splitting hairs. I'm just going to keep it as an array and kind of use the most straightforward. So now what we're going to do is we're just going to kind of flip things a bit. So all we got to do is put the out RGBA on the other side. And then array seems like a pretty nice choice here because we already have arrays here. So, lining everything up is pretty easy. All we got to do is match these numbers. In fact, we could just do this. Copy here, paste here, and then boom. No typos, right? We got it, And if you want to be extra careful, double click, make sure everything highlights as expected. And then we're not going to... Well, I have I have a return here because I thought I was going to do it that way, but we're not. We're going to do it that way. And now that we know that that's kind of like the signature, we're going to go up to get picks. Okay, that looks good. I'm going to check, make sure I didn't make any syntax errors, just refresh, make sure nothing's crashed. That still looks good. Okay, so we have this getter function. I haven't tested it, but I'm fairly convinced that it'll work. And we need to just move on with the sampling code. And then if once we get the sampling code to work, then by default we'll know that the get pixel code works. Okay, so let's go back up to where we're looping through everything where we don't have anything yet. And I think now we got to start thinking about the math. Okay, yeah, so let's do that. We can just write the math here for now. Basically, what we want to do is let's open up the picture. We want to convert a point right here. We want to convert an XY point within this viewport to a %X, %Y within this region, right? So, right in the exact center is 50%, 50%. And then we can do the same thing over here, right? And the exact center would be 50%, 50%, right? And then something like 75%, 75% would be like over here, which would be kind of like over here, right? And that's how we're going to get that mapping. Now the thing is, how do we write a formula where it's kind of like a one-liner, right? Like a very, because we could like drag this out into multiple statements to do this, but if we do a little bit of algebra, we can probably get this in like one nice, neat equation, as we are seeing on this page on like a Stack Overflow, or well, not Stack Overflow, math.stack exchange, which is just like it's still kind of like Stack Overflow, but it's like a sub community of Stack Overflow or something like that. Anyway, so let's go back here. And let's start writing the code. So first thing, we want to figure out percentages for both of the rectangles. So the first thing I'm going to think about is okay. So I'm going to say SRC. Okay, I'm just thinking of variable names here. Let's say S x0 is for the rectangle source dot x0. Paste that a few times. And then 0, 1, 0, 1, put some y's down. And then take that. Ooh, well, no, we can't do that. Take this, paste that there. Take our y's. Oops, take our y's. Paste that there. Right, so now we got all of the points. And now we'll do the same thing with the destination. So we have our source and the destination. So source and destination. And DST. So we got to put a DST right there. DST. Okay. Source, dest. So we got these nice little terse variables that we can juggle around in equations now. So since we've done that, we probably should, since these variables here are the ones we're going to want to work with, I think it would be more readable to use substitution and replace these with their respective variables now. So we got our dx0. So destination x0, destination x1, and then our destination y0, and then our destination y1. And I like that because these lines are much shorter now. And now when we like double click these, right, we can see where they're all coming from, right? We can see the connection a little bit quicker because we have less mental indirection. Okay, so let's say that the percentage DST equals what? We have to take, what do we have to do to get a percentage of the x? Yeah, so I guess per DST x, destination x, I'm just call it dpx, destination percent x, and there'll be a dpy. I can say destination percent x, and so we're going to take x, and we need to make x start. We need to translate the coordinates so that they start at 0, 0. X minus dx0 and then it's going to be all over and dx1, so the greater value, and then minus dx0 as well. So I'm trying to explain this. So if x is at the beginning of the rectangle, then that means x is at dx0, right? And then that means x minus dx0, that's going to be 0, right? And dx1 minus dx0 is the entire range. So let's say that the rectangle is 100 pixels wide, correct? And let's say that x is currently 0, which means it's at the top left. That would be 0 100ths. 0 100ths being 0% in terms of where it is in percentage coordinates. Now, if x makes it all the way over to the other side of the rectangle, that means x will now equal dx1. So that means that this part is going to be, right, x equals dx1, which means that we can take this dx1 and put it here, right, because they're both equal. And now we have two identical equations, which would be 100 over 100, which is equal to 1. So 100 100ths is 100%, right? So that's how we're going to get that percentage. Now, we're going to want to expand. Let's just stick with this for now. So we know. So what I'm going to do is I'm going to put it in a one line like this. And I'm going to make this into a comment, because I'm actually not going to use the code exactly like this. This is just kind of to get us started somewhere. Because what we want is a mapping from one canvas to the other using the percentage coordinates. So really what we want is something like this, where this is our destination, and then our source is, hold on. Okay. So all of this is a percentage. And so we want the percentage coordinate on this canvas to be the same as the percentage coordinate on this canvas. Okay, so let's go back. I think I need to look at the equations a little bit more. So I'm going to say dpx equals this. And then we're going to say source, and then we're going to make these into s's. And then we're not, this x here is not in terms of percentage. Oh, sorry. Can you? Oh, no, you can see it. Okay. This x is not in terms of percentage, correct? This is actually what we want to solve for, this x right here. So to make this clearer, I think what I'm going to do is I'm going to prefix these with d's for destination. Okay, right. So destination x, destination y. And then we're going to put that dx there like that. Right. So destination percent x equals the destination x minus that lower bound divided by the length, right? Okay, so we got these two formulas, and right, this is going to be source x. And we want to solve for source x, right? So let's take this formula, and we're going to comment this out like that. And we're going to set these equal to each other. And we're okay, timer went off and it startled me. We're gonna compact this a little bit because I don't want to leak over the screen when I'm doing this. So equals, right, and we're gonna solve for this one right there. Because basically, okay. So what's the first thing we can do? What do we know? What don't we know? Well, these values we know, right? They are the bounds of the x bounds of the rectangle, right? Of the source rectangle. So what we can do, we're going to duplicate this line, and then we're going to multiply both sides. I guess multiplication, well, let's not risk it. Let's not risk it. So, all right, let's just do that. And now that we have that, let's put that there. Okay. And now that we have this, we are gonna we can take off those parentheses. Okay, let's duplicate the line again. And remember, we're solving for this, right? We're solving for sx0. Wait, we're not solving for... Yeah, we are. Hold on. Minus. Okay, yeah, okay. So minus sx0. Minus x0. Man, I need better algebra skills. So how do we remove this if it's on that side? Right, because we just want to get that onto the other side. I believe this would be something like 0 plus so we could think of it as I believe we can we just get rid of that? Okay, I'm gonna refresh some algebra skills and then get back to this. So I'll be right back, because this is pretty trivial basic stuff, but it's been a while.